Okay, so far we learned several way to solve the first order ODEs. So separable, method of integrating factor, and the exact solution, and then the homogeneous, and so on. So today I'm going to introduce the fundamental numerical method, which is a little bit better than improved Euler method, better than improved Euler method. This is called the improved Euler method. So let me derive the formula for the improved Euler method. So y prime is equal to f of t comma y. And let me start with this. This is the kind of, um, the standard form of the first order ODEs with initial conditions y of t0 is equal to y not. Okay, that's the initial condition. So we're going to consider the initial value problems. So let's say the domain of y, here y is unknown function. Domain of y in is the 0 t0 to the t sub n plus 1, which means that we divide, let me say this is t, okay? So divide the interval into the n plus 1 subintervals. Okay, so it is n subintervals, sorry. That is t1, is t2, is t3, through d. Here is maybe tn. Okay, so tn plus 1, and so on. And then up to tn plus 1. So n, so we divide time interval or domain, you can say that time interval into n subintervals. Okay, so here now the length of each subuniverse, let's say the length of each subuniverse be h. So from here to here, that's the h. So which means that h is t sub n plus 1 minus tn in general. So n goes 0 through the n, right? Okay, so keep like this. Okay, so now to get the formula for the improved Euler method, we're going to take integral of that differential equation. So take integral t sub n, the t sub n plus 1. So take integral of the both sides of the differential equation on tn and tn plus 1. And we got this equal to t sub n, the t sub n plus 1, and the f of t comma 1 dt. Then implies, so as you can see that the left-hand side is the anterior derivative y, right? So by the fundamental theorem calculus, we got this one, y sub tm plus 1 minus y of t sub n. Because the fundamental theorem calculus, let me say this FTC. That means fundamental theorem of calculus. Fundamental theorem of calculus. So this is equal to, okay, this is equal to t, let me just copy the right-hand side. Okay, tn plus 1, and then f of t comma y, and the dt. Okay. Now, to handle this one, because, we do not know the anterior derivative f. So, we got this kind of problem, right? Because how can you evaluate that integral since we do not know the anterior derivative f? So we need to approximate that integration somehow. So we just replace tn to tn plus 1, I mean the right-hand side of here, this equation, with this. Okay, so we're gonna replace this one with this one. So what is this? So it means that means, let me see, give me a second. So give me a second. Yep. So let me draw the f of t comma y. Okay. So let's say here is a t. Okay. And that's the f. Okay. Then maybe graph is maybe like this. So f of t comma y. So how can you guarantee that, the graph of, I mean, the function f is continuous? Because when you start when you define that initial value problems, we assume that this initial value problem exists, there exists solution, which means that by the existence and uniqueness of the initial value problems, we already assume that f is continuous and actual continuous, and then f derivative also continuous on that interval, time interval. So since by that assumptions, we can say that we can draw the graph of f is like this. Okay, so keep in mind that. Now let's say Tn is right there, and then here's a Tn plus one. Okay, give me a second. Let me put Tn here, and then here's a Tn plus one. Okay. So the integral, just take a look at the definite integral. Take a look at the definite integral of f from Tn to Tn plus one. Then that means what? That's going to be area of area under the graph of f from Tn to Tn plus one, right? Sorry. So it should be this one. Okay, give me a second. Let me change. Just move to Tn plus one to left a little bit. So graph is like this. Okay. So that's the integral Tn, Tn plus one, and the apple T comma y and dt. Now we're gonna approximate the area with that rectangle. Okay. I know there is some kind of big gap. So you see clearly there is a difference between the area of the, that area, I mean, the area of the box rectangle with the area of actual value of that integral. But as h, you see this is h, right? As h goes to approach zero, that error will be decreased. Okay. So still we can say that r, say this is area is, let's say this r, okay? That r must be can be used as approximation of that definite number. And then now the what's the area of the rectangle? Just h times, the height gonna be, you see that? It's gonna be what? It's gonna be f of t sub n, right? Comma y sub n. So you can see that right here. So this is the f of t n comma y sub n. Okay. And then right there, it's gonna be, give me a second. It's gonna be f of t n plus one comma y sub n plus one. Oh, y sub n plus one. Yes. Okay, sorry. Give me a second. Okay. All right. Okay. So now, so R is gonna be, this means the area of rectangle going to be h times what? F of t n comma y sub n, isn't it? So this is exactly the same as this. So we use this one as approximation of that integral. Okay. So the now that we got this one from here, Give a second. You see this one in this formula. Ooh, ooh, okay. Yeah, in this formula, what we just isolating the y of tn plus 1, so move y of tn to the right hand side, and then replacing that integral with this one, which is approximation, I mean area of the rectangle, then we got this. Y sub n plus 1 is equal to y sub n plus h times f of tn comma y sub n. That's the Euler method, actually. So this is Euler method. Okay. The next one, so I made, just as I mentioned that there is a big the gap between here to here, right? So how can you reduce that error? I mean, the difference between the approximation, I mean, the area of rectangle and then, actual value of that integral. How can you reduce this much of difference? Then to as one, as one of the method way to reduce that, we're gonna choose not, the point at Tn, but we're gonna choose the average of 2 points. So pretty much we choose maybe this point. Okay, so that's gonna be f of Tn comma y sub n. Give me a second, sorry. So let me move this one to right here. Gonna be f of Tn comma y sub n plus f of Tn plus 1 comma y sub n plus 1 over 2. Over 2. Is it? Okay. To do that, then what? Let's say, then we got this one. Then let me use other color, maybe yellow here. Then we got that rectangle. This rectangle right here. Therefore, this is much close to, I mean, much closer to this one rather than this. You see? Okay, so let me derive the formula of the for the formula for the approximation of the the solution using that average point. Okay, so now here y sub m plus 1 is equal to m plus 1 is equal to y. So you see that right here? What? But this is what we use the area rectangle. That's the area rectangle, right? So we're gonna replace substitute this one into here. Okay, I mean replace this one with that. So now then yn plus, instead of that, we're gonna get what? This. Let's see here, h times. Okay, h times. Give me a second. By the way, the area of the yellow box is the what? Area of the yellow box is h times f of Tn comma y n plus f of Tn plus 1 comma y sub n plus 1. We need more space. Y sub m plus 1 over 2. Okay, that's the area of, let me say this, let's say this is r prime, maybe r prime, okay, is equal to this. So we use that one instead of this one. So this formula this one, I mean, that formula, Euler method, will be changed to this h times f of t n comma y sub n plus f of t n plus 1 comma y sub n plus 1 over 2. Okay. Okay, here's problem. What do you think the problem is? Since here in this formula, this is an implicit method or implicit scheme. Let me just put implicit scheme. Okay. Now this is equal to what? Y sub n plus, since the unknown, the y sub n plus 1 is unknown, right? That's what we want to find out. But y sub n plus in the formula. So that's why this is implicit scheme, right? So now we approximate this one with the Euler formula. Then we get this h y sub n plus h times f of t n comma y sub n plus, you know, f of, I mean, t n plus 1. Why is t sub n plus 1 is what? Is also t sub n plus h, right? Okay. Comma y sub n plus 1 is y sub n plus h times f of t sub n comma y sub n over 2. So right here, the y sub n plus h times f, that's the Euler method. I mean, this is approximation to y sub n plus 1 by Euler method. Okay. Now this is equal to, oh, by the way, that's gonna be how we got this, because this is equal to what? T sub n plus 1. Okay. So finally we can say, use other color, maybe this one. So y sub, I mean, this is y sub n plus 1 is equal to y sub n plus, and then h over 2 times what? F of t, let me say f sub n, which represent the which denote the f of t sub n comma y sub n. F sub n plus f of t n plus h comma y sub n plus h times f sub n. False. Okay. So that's the improved Euler method. That's the improved Euler method. See, a second. Where f sub n means f of t n comma y sub n. Okay. Okay. Good. Okay. What's the difference between, I know, so formula is a little bit complicated, more complicated than the Euler method. But what's the difference between that improved Euler method and then just Euler method? By the way, this is improved method. So Euler method has the convergence rate of equal h squared. Let me write down. Euler method. versus improve. The Euler method BOH. It means that big O means that that's the constant times H. Okay, maybe 2H, 3H. Okay, just constant times H. That means a big OH. We don't know what constant is, what coefficient is, but this means the multiple of H. In proof of Euler method, the convergence rate is big OH squared. Okay. So what does that mean, convergence rate? So convergence rate means that convergence rate means that if H is decreased, let's say H is 1, right? Okay, so we got the y sub n plus 1. The accuracy y sub n plus 1, okay, and then we reduce H by half. Then the accuracy will be decreased by 1/2. Sorry, error will be decreased by 1/2. Okay, so H is decreased by half, then accuracy will be increased by twice, which means the error will be decreased by 1/2. That's a big O H. But improve Euler method, as H is decreased by half. Okay, give me a second. The error. Let me say E is the error of y sub n plus 1. Then big O H, we're going to get E over 2. The error will be decreased by half. But improve Euler method, big O H squared, which means that H decreased by 1/2. Let's say E is the error of y sub n plus 1. Then decreased by 1/2. Then error will be decreased by not half, but half squared. So we got E times 1/4. Or you can say 1/2 squared. This is also E over E times 1/2. 1/2. Okay. So improve Euler method, when you decrease the H time step size, we're gonna get the much better accuracy solution, which is much better accuracy than the Euler method. Okay. That's why we are interested the numerical method with high order of convergence rate. Okay. So can you get the big, something numerical method, which is better than big O H squared? There is big O H to the fourth, maybe big O H to the fifth, maybe more. Okay, but there is some, but something you need to, it comes cost, maybe more computation or it's more restriction. Okay, so we talk about this one in a numerical method class. Okay, but just leave it and then let me introduce the other one. Before doing that, let's see example. Example. So example is example 2 in textbook. Okay, so use the improve Euler method. Okay. To find to approximate the solution to the initial problem. Okay, y prime is equal to x plus 2y. So now this is the y. That's the f of x. This is f of x comma y. And then the problems give us the initial condition y over 0 is equal to 0.25. Okay, so and then they also give a tolerance. Right, the initial value problem. Sorry, at x equals 2. Sorry, I didn't finish the writings, the problems, and the tolerance. Epsilon, this is epsilon. Epsilon is 0.001. What's the tolerance? Tolerance is that it means that here we want to find out approximation with accuracies within epsilon, which means that if we say y of y super h is approximation obtained by Euler method, improved Euler method, y superscript h at x equals 2 minus y of 2. So this is approximation. This is the exact solution. Then errors, there's error, right? Error must be, we want to find out such an approximation where the error is less than 0.001. I mean, epsilon. Okay. But how can you find it? You need to adjust the step size h. You see that input Euler method, when you decrease the steps times step size h, then we got a lot better accurate the better accuracy, right? Solution that have a lot of better accuracy. So now we start with the here step 0. We need to find out step 1. Okay, step 1. We need to find out the formula. What is that? We need to figure out the right-hand side of the input Euler method formula. Okay, so what is because we know f, right? So we can figure out this. Yeah, first of all, we need to partition the innover. Okay. 0 to 2, 0, 2. Okay. So here's a 0. Here's a 2. Let's say this is x of n. Okay. Let's say this is x of 0. Okay. You can say x of n plus 1, doesn't matter. Okay. So now here is the x of 1. Here's x of 2 through d. Maybe here's x of k and x of k plus 1. You can say, you can use a lowercase n, okay? It doesn't matter. So now in the step 2, so f will identify the function f, which is 2x plus 2y in this problem. Then y sub n plus 1 is equal to y sub n plus h over 2, right? And then you see that formula is quite long, right? So let me make it short. Okay, using new notation, y sub n plus y sub n plus 1 star. Okay. Okay. Let's see. So this is equal to what what is it? Y sub n plus 1 star. That represent, okay, this one. One second. Okay. So give me a second. Okay. Oh, by the way, did I miss that? This should be f, right? Fn. Yeah. Sorry, it's confused. It should be Fn. Okay, let me just use the F star. Okay. So that means, as you can see here, that means this one. Okay. Okay. So this means y sub n plus h times f sub n by the Euler formula. Euler method, right? So this is equal to y sub n plus h over 2. And then, okay, so what is f sub n? F sub n is what? What is f sub n? Hmm? F of x comma y is x plus 2y, right? So f sub n is going to be what? F sub n is equal to f of t sub n and y sub n. Right? So this is equal to, oh, here we use x, right? Instead of t, sorry. So we got x sub n plus 2y sub n, right? So this is equal to x sub n plus 2y sub n, and then plus y sub n, is it? You got it? Do you follow me? No? And then the plus h times, right? And then f sub n. So here f sub n is this. That is equal to x sub n plus 2y sub. Is it? Okay. Okay, so I just derived the formula of the problem that specifically given the function f of x comma y is given the problems. I derived the input Euler formula for this problem in particular. Now the here we're gonna go over the we're gonna see Taylor higher order numerical method, Taylor method, and the Wunsch method.